For nearly 40 years, we thought we knew what Uranus looked like. A pale blue marble, smooth, quiet, featureless. The single photograph burned into every textbook came from a spacecraft that spent barely 5.5 hours at the planet and happened to arrive during a once-in-a-generation solar storm that compressed and distorted everything it measured. That was Voyager 2. That was 1986. That was all we had. Then the James Webb Space Telescope turned its infrared eye toward the seventh planet, and what it revealed was not the same world. Rings emerged from the darkness. Auroras twisted through a lopsided magnetic field. A polar cap glowed where no light should reach. And a 29-moon system appeared where Voyager had seen almost nothing. The quiet planet was never quiet. We just could not see it. If you enjoy deep dives into real science that changes how you see the universe, take a moment to like and subscribe. Also, before we begin, we're now live on Spotify. The link's in the description if you'd like to listen to us wherever you are. Now, are you comfortable? Let's begin. There is a photograph that nearly every human being alive has seen at least once. It appears in elementary school textbooks, on posters in science museums, on the background screens of documentary television specials about the outer solar system. It shows a pale blue-green sphere, smooth, calm, completely featureless. No storms, no bands, no swirling hurricanes or dramatic atmospheric structures. Just a soft, round, almost eerily clean ball of muted color hanging in the blackness of space. That photograph was taken on January 24th, 1986, by a spacecraft called Voyager 2. And for nearly 4 decades, it defined everything the human species believed about the seventh planet from the sun. Uranus was the boring one. That was the consensus. Not just among the general public, but among scientists, educators, and even planetary researchers who studied the outer solar system for a living. Jupiter had its great red spot, a storm larger than Earth that had been raging for centuries. Saturn had its rings, arguably the most visually stunning structure in the entire solar system. Neptune, which Voyager 2 would visit 3 years later, had the great dark spot and winds screaming at over 1,000 miles per hour. Even tiny Pluto, barely a speck at the edge of everything, generated passionate debate about its classification. Uranus generated almost nothing. It sat in the public imagination as a placeholder. A planet that existed mostly to fill the gap between Saturn and Neptune. A world so unremarkable that its most famous quality was the way people mispronounced its name. That reputation was not earned through careful study. It was earned through a single visit, under conditions that were nothing close to normal. And the story of how that visit created one of the longest-running misunderstandings in planetary science begins not at Uranus itself, but at a launch pad in Cape Canaveral, Florida, 9 years before the spacecraft ever arrived. On August 20th, 1977, a Titan IIIe Centaur rocket lifted off carrying Voyager 2, the first of 2 identical spacecraft designed to take advantage of a planetary alignment that occurs once every 175 years. Jupiter, Saturn, Uranus, and Neptune were arranged in a configuration that allowed a single spacecraft to visit all 4 worlds using gravity assists, slingshotting from one planet's gravitational pull to build speed toward the next. The window for this alignment was narrow. Miss it, and the next opportunity would not come until the 22nd century. Voyager 2 was originally approved to fly past Jupiter and Saturn only. The Uranus and Neptune legs of the journey were additions, approved after the spacecraft proved it could survive the radiation environment at Jupiter and still function. This matters because it means the entire Uranus encounter was, in a real sense, a bonus. The spacecraft was not purpose-built for studying ice giants. Its instruments were designed for the radiation-heavy, magnetically intense environments of Jupiter and Saturn. Its cameras were optimized for the light conditions near those two gas giants, where the sun was closer and illumination was stronger. By the time Voyager 2 reached Uranus, it was operating in an environment 400 times dimmer than Earth's surface. The cameras struggled. The exposure times had to be dramatically extended, and engineers on the ground developed new techniques to compensate. Rotating the spacecraft during exposures to avoid motion blur in the low light conditions. The engineering challenge deserves more attention because it shaped everything Voyager could and could not see. At Jupiter, where the sun is roughly 27 times brighter than at Uranus, the cameras could take rapid exposures with short shutter times, freezing atmospheric motion cleanly. At Saturn, the light was dimmer but still workable. By the time Voyager 2 reached Uranus, the illumination had dropped to a level where the cameras needed exposures so long that the spacecraft's own motion during the shot would smear the image into uselessness unless something was done. The solution was a technique called image motion compensation. Engineers at the Jet Propulsion Laboratory reprogrammed the spacecraft's attitude control system so that during each long exposure, the entire spacecraft would slowly rotate to track the target, keeping it fixed in the camera's field of view, the way a photographer pans a camera to follow a moving car. This was not a capability the spacecraft was designed for. It was invented on the fly, uploaded to a vehicle more than 1.5 billion miles away through a radio link with a round-trip signal delay of over 5 hours. If the commands contained an error, there would be no second chance. The flyby geometry was fixed. The window was closing. The technique worked. The images Voyager returned from Uranus were sharper than anyone had a right to expect, given the conditions. But working within those constraints meant trade-offs. Longer exposures captured more light, but limited how many images could be taken in the narrow flyby window. Every frame pointed at the planet was a frame not pointed at a moon, a ring, or the magnetospheric environment. The Voyager team had to make choices about what to photograph, and those choices were driven by the need to preserve the option of a future encounter with Neptune. The trajectory that would carry Voyager 2 onward to Neptune in 1989 dictated the geometry of the Uranus flyby. The spacecraft could not linger. It could not loop back. It could not slow down. It passed through the system on a fixed path, at a fixed speed, grabbed what it could, and kept going. The encounter itself was staggeringly brief. Voyager 2 had 5.5 hours of close-range study time at Uranus. That is not 5.5 days, not 5.5 weeks. 5.5 hours to study an entire planetary system, its atmosphere, its magnetic field, its rings, and its moons, before the spacecraft's trajectory carried it onward toward Neptune. The closest approach brought Voyager 2 within roughly 81,500 kilometers of Uranus's cloud tops. In the scale of interplanetary distances, that is close. In terms of what you can learn about an entire world in a few hours at that range, it is barely a glance. And what that glance revealed was underwhelming. At least, that is how it appeared. The visible light cameras returned images of a planet that looked almost deliberately blank, where Jupiter showed turbulent bands and enormous storms. Uranus showed a nearly uniform blue-green haze. Image processing teams at the Jet Propulsion Laboratory in Pasadena pushed the contrast as far as the data would allow. They found faint, low-contrast cloud bands and a tiny handful of discrete cloud features, so subtle they were invisible without extreme enhancement. The planet looked like a billiard ball dipped in blue paint. One of the Voyager imaging team members later described the disappointment as palpable. After the visual spectacle of Jupiter's churning atmosphere and Saturn's intricate ring system, Uranus was a blank wall. The spacecraft did make genuine discoveries. It found 10 previously unknown moons, bringing the total at the time to 15. It detected 2 new rings in addition to the 9 already known from ground-based observations. It measured the planet's rotation period at roughly 17 hours and 14 minutes. And it made one of the strangest findings in the history of planetary exploration. The magnetic field of Uranus was tilted 59 degrees away from the planet's rotational axis and was offset from the center of the planet by roughly 1/3 of its radius. No other known planet had a magnetic field this misaligned and this displaced. It was as if the magnetic core of the planet had been knocked sideways and shoved off to one side. That was genuinely shocking, but the public never latched onto it. Magnetic field geometry does not make for gripping television. What made it onto the evening news was the photograph. The pale, smooth, featureless sphere. The boring planet. And then the world moved on. Here is what almost nobody understood at the time, and what most people still do not understand today. Voyager 2 did not see the real Uranus. It saw Uranus during a moment so atypical that the data it collected may have distorted our understanding of the planet for 4 decades. In November of 2024, a study published in Nature Astronomy by Jamie Jasinski, a physicist at NASA's Jet Propulsion Laboratory, dropped a finding that reframed the entire Voyager encounter. Jasinski and his team went back to the original 1986 data and reanalyzed the solar wind conditions at the time Voyager 2 crossed into Uranus's magnetosphere. What they found was that the spacecraft arrived during a solar wind compression event. A surge in charged particles streaming outward from the sun that dramatically altered the magnetic environment around the planet. The solar wind dynamic pressure at the time of the flyby was roughly 20 times higher than what Uranus would normally experience. This extreme pressure compressed the planet's magnetosphere to approximately 20% of its typical size. Imagine a balloon being squeezed by a fist. The shape changes. The internal pressure shifts. Everything inside rearranges. That is what happened to Uranus's magnetic bubble while Voyager 2 was passing through it. The consequences of this compression were not trivial. The magnetosphere appeared to be severely depleted of plasma, the charged particles that normally populate a planet's magnetic environment. For decades, scientists interpreted this emptiness as a fundamental characteristic of Uranus. They concluded that the planet's magnetosphere was inherently barren, that its moons were inactive, and that the system lacked the dynamic processes seen at Jupiter and Saturn. Jasinski's analysis showed that conclusion was almost certainly wrong. The spacecraft saw Uranus in conditions that occur roughly 4% of the time. That means 96% of the time. The magnetosphere looks completely different. Larger, more populated, more dynamic. If Voyager 2 had arrived just a few days earlier, before the solar wind surge hit, it would have encountered a magnetosphere potentially 5 times larger, with a fundamentally different plasma environment. The moons that appeared inactive might have shown signs of particle interactions. The radiation belts that seemed inexplicably intense might have had a clearer explanation. The entire scientific narrative about Uranus's magnetic system might have been different. This is the part that should disturb you. For nearly 40 years, the canonical understanding of Uranus, the version taught in universities, cited in research papers, referenced in mission planning documents, was built on a snapshot taken during a rare event that does not represent the planet's normal state. It is as if a doctor examined a patient during a once-in-a-decade allergic reaction, and then wrote in the medical chart that the swelling, the redness, and the distorted features were the patient's permanent condition. Every subsequent doctor who read that chart would treat the patient based on a distortion. Linda Spilker, a NASA scientist who was present during the original 1986 flyby, responded to Yasinski's findings with a statement that carries quiet weight. She said the new work explained some of the apparent contradictions, and that it will change our view of Uranus once again. Once again. Because the view had already changed before. Ground-based telescopes equipped with adaptive optics have been watching Uranus for years and seeing things Voyager never showed. Storms, bright cloud features, atmospheric activity that increased as the planet moved through its 84 Earth-year orbit. The bland blue ball was not holding up to closer inspection, even before the James Webb Space Telescope entered the picture. This should have been the moment the scientific community fundamentally reassessed its picture of Uranus, and in some corners, it was. Planetary scientists who specialized in ice giants published papers throughout the 2000s documenting the atmospheric changes, noting bright cloud features appearing in near-infrared observations from the Keck Observatory and the Hubble Space Telescope. In 2006, a dark spot appeared in Uranus's atmosphere, detected by Hubble, the first such feature ever observed on the planet. By the time of the equinox in 2007, when the sun was shining directly on the equator and both hemispheres were experiencing roughly equal illumination for the first time in decades, the atmosphere was visibly more active than anything Voyager had recorded. Wind speeds were measured at up to 560 miles per hour in certain atmospheric bands. Cloud features tracked across the disk showed complex circulation patterns that varied with latitude. The planet was not a smooth, well-mixed sphere. It had weather. It had structure. It had dynamics that responded to the changing seasons in ways that demanded explanation. But these observations lived mostly within the specialist literature. The general public, the textbook publishers, the documentary filmmakers, and even many scientists outside the ice giant community continued to rely on the Voyager image as their mental model of Uranus. The photograph was too iconic, too widely reproduced, too deeply embedded in the cultural memory of what the outer solar system looked like. A faint cloud feature detected by Keck at 3 in the morning on Mauna Kea could not compete with a NASA press photograph distributed to every newsroom on Earth in 1986. But the Voyager image persisted. It persisted because it was the only close-up humanity had ever taken. It persisted because first impressions are powerful, especially in science, where the initial data set becomes the foundation on which all subsequent work is built. And it persisted because nobody sent another spacecraft. That last point deserves emphasis. In the nearly 4 decades since Voyager 2 flew past Uranus, no space agency on Earth has sent a dedicated mission to the 7th planet. Not NASA, not the European Space Agency, not any other organization. Every other giant planet in the solar system has received follow-up attention. Jupiter got Galileo, then Juno. Saturn got Cassini, which orbited for 13 years and revolutionized our understanding of the ringed giant and its moons. Even distant dark Neptune is at least discussed as a future target. Uranus sits in a category of its own, the least visited major planet in the solar system. A world whose entire body of close-range data comes from 5.5 hours in 1986, during a solar storm that warped the measurements. To understand why this neglect matters, you need to understand what Uranus actually is. Not the cartoon version, not the textbook placeholder, the physical object. Uranus is an ice giant. That term itself is relatively new. For most of the 20th century, Uranus and Neptune were grouped with Jupiter and Saturn as gas giants. But they are fundamentally different. Jupiter and Saturn are composed primarily of hydrogen and helium, the lightest elements in the universe, compressed into liquid and metallic states under enormous pressure. Uranus and Neptune are smaller, denser, and composed largely of heavier compounds. Water, methane, and ammonia in states so compressed and so hot that calling them ices is almost misleading. Deep inside Uranus, these materials exist under pressures millions of times greater than Earth's atmosphere, squeezed into exotic phases that do not occur naturally anywhere on our planet's surface. In 2018, physicists at the Laboratory for Laser Energetics at the University of Rochester used one of the most powerful laser systems on Earth to compress water to pressures and temperatures comparable to those found deep inside Uranus. What they observed was a state of matter that had been theorized for decades, but never directly confirmed. The water molecules broke apart under the extreme conditions, and the oxygen atoms locked into a rigid crystalline lattice, forming a solid framework. But the hydrogen atoms, stripped of their electrons, did not lock in place. They flowed freely through the oxygen lattice like a liquid moving through a cage. The result was a material that was simultaneously solid and liquid, a crystalline structure that conducts electricity like a metal because the free-flowing hydrogen ions carry charge through it. Scientists call this state superionic ice. It is not ice in any sense you would recognize. It is not cold. It is not brittle. It exists at temperatures of thousands of degrees and pressures millions of times greater than Earth's atmosphere. And it may constitute a substantial fraction of Uranus's interior, forming a thick shell between the rocky core and the outer gaseous envelope. If superionic ice does make up a significant portion of Uranus's mantle, it has direct implications for the planet's magnetic field. The flowing hydrogen ions within the superionic layer would act as an electrically conducting fluid, capable of generating magnetic fields through convection, but in a shell-like geometry rather than the deep core dynamo that drives Earth's field. This could explain why Uranus's magnetic field is offset from the center of the planet and tilted so severely from the rotational axis. The field is not being generated at the core. It is being generated in a shallow, off-center conducting layer made of a material that exists nowhere else in the observable solar system, except inside ice giant planets. The blue-green color that Voyager photographed comes from methane in the upper atmosphere. Methane absorbs red light from the sun and reflects blue and green wavelengths back into space. That much was straightforward. But the color told scientists almost nothing about what was happening below. The visible light image was, in effect, a photograph of the top of a cloud deck. Everything beneath it, the storms, the circulation patterns, the thermal structure was invisible to Voyager's cameras. The planet is enormous by human standards. Its radius is roughly 4 times Earth's. You could fit 63 Earths inside it. Its mass is 14.5 times that of Earth. It orbits the Sun at a distance of roughly 1.8 billion miles, so far away that sunlight takes approximately 2 hours and 40 minutes to reach it. At that distance, the Sun is not a blazing disk in the sky. It is a bright point of light, intense enough to create day and night, but dim enough that Voyager's cameras had to fight for every photon. And it is cold. Uranus holds the record for the coldest measured temperature of any planet in the solar system. Its atmosphere has been measured at roughly minus 224 degrees Celsius, colder even than Neptune, which orbits 1 billion miles further from the Sun. That fact alone is strange. A planet closer to its star should not be colder than one farther away. And the explanation, or rather the lack of a complete one, points to something unusual about how Uranus manages its internal heat. Most giant planets radiate significantly more energy than they receive from their star. Jupiter, Saturn, and Neptune all emit far more heat than sunlight alone can account for, driven by residual warmth from their formation and by ongoing processes deep in their interiors. Uranus is the exception. It radiates almost nothing beyond what it receives. Its internal heat source, if it still has one, is either extraordinarily weak or somehow trapped beneath layers of atmosphere that act as insulation. Nobody fully understands why. Several hypotheses have been proposed. One suggests that the catastrophic impact that knocked Uranus onto its side, the event believed to have caused its extreme 98-degree axial tilt, also disrupted the planet's internal heat flow, creating a stratified interior where hot material cannot rise efficiently to the surface. Another suggests that the composition of the deep atmosphere traps heat in ways that the simpler hydrogen-helium envelopes of Jupiter and Saturn do not. A third suggests that whatever process generates internal heat in the other giant planets simply ran its course earlier in Uranus's history. None of these explanations is confirmed. The data to distinguish between them does not yet exist, and that is the recurring theme with everything about this planet. We do not have the data. Voyager 2's 5.5-hour flyby during a rare solar wind event, using instruments designed for brighter, closer, more magnetically familiar planets, is the only close-range dataset that exists. Every model of Uranus's interior, every simulation of its atmospheric dynamics, every prediction about the behavior of its rings and moons is built on a foundation that was compromised from the moment it was collected. Not because the Voyager team did anything wrong. They performed brilliantly with the tools they had and the time they were given. But because a single brief visit during anomalous conditions is not enough to understand a world. Imagine photographing a stranger at the exact moment they sneeze. The image is real, the data is accurate, but if you use that photograph to describe what the person looks like for the next 4 decades without ever seeing them again, you have built your understanding on a distortion. You have mistaken the exception for the rule. That is what happened with Uranus. The planet sat in the outer solar system, rolling along its orbit on its side, cycling through its bizarre seasons, churning with atmospheric processes that no camera was watching, surrounded by a ring system that no telescope could resolve in detail, accompanied by moons whose surfaces hinted at geological histories that no instrument could confirm. All of it unfolding in darkness and distance, while the scientific world collectively shrugged and moved on to more photogenic targets. Then, in the early 2020s, something changed. A telescope unlike anything humanity had ever built reached its observation point 1 million miles from Earth, unfolded a gold-plated mirror 6.5 meters across, cooled its instruments to temperatures colder than the space surrounding it, and turned to look at the outer solar system. It did not see the same planet. The James Webb Space Telescope operates in infrared wavelengths. It does not see the universe the way human eyes do, and it does not see Uranus the way Voyager's visible light cameras did. Where Voyager saw a smooth blue sphere, Webb sees thermal emission, chemical structure, atmospheric layering, and reflected infrared light that penetrates through the haze Voyager could not see past. The difference is not incremental, it is not a slightly better version of the same picture. It is a fundamentally different kind of observation that reveals a fundamentally different planet. The first Webb image of Uranus, released in April of 2023, was a 12-minute exposure using just 2 filters. Even at that brief duration, it showed something no human being had ever seen in this level of detail. The rings of Uranus emerged from the darkness in sharp clarity. Not just the main rings, which have been known since the late 1970s, but the faint, diffuse inner rings, including the elusive Zeta ring, the closest ring to the planet, so dim that only 2 other facilities had ever detected it. Voyager 2, during its 1986 flyby, and the Keck Observatory in Hawaii, using adaptive optics decades later, Webb captured it in a fraction of the exposure time. But the rings were only the beginning. The image showed the seasonal North Polar Cap, a bright white region near the pole currently tilting toward the sun, as Uranus approaches its next solstice in 2028. Within that polar cap, Webb revealed a structure Voyager had never detected. A bright inner core surrounded by a dark lane and bordered by faint, extended features. Bright storm clouds appeared at the edge of the cap. 9 moons were visible in the close-up view. 14 appeared in the wider field. A subsequent Webb image released in December of 2023, using longer exposures and additional filters, deepened the picture further. More storms, more atmospheric features, more detail in the ring structure. Background galaxies appeared scattered around the planet, a reminder of the telescope's extraordinary sensitivity, picking up light from billions of light years away in the same frame as a planet in our own solar system. This was not a modest improvement over Voyager. This was a reclassification. The featureless blue ball was gone. In its place was a ringed, stormy, structured world with visible atmospheric dynamics, a glowing polar cap, and a system of moons scattered like dust across the field of view. And Webb was just getting started, because the still images, as dramatic as they were, captured only a frozen moment. What followed in 2025 was something far more revealing. An observation campaign that watched Uranus rotate for 15 continuous hours, mapping its upper atmosphere in 3 dimensions for the first time, detecting auroras no one had ever resolved, and confirming a cooling trend that nobody can fully explain. The planet Voyager left behind as a pale, quiet mystery was about to become something else entirely. To understand why the James Webb Space Telescope sees a different Uranus than Voyager 2 did, you first need to understand what infrared light actually is. and why it matters so profoundly for a planet sitting nearly 2 billion miles from the sun. Every object in the universe that has a temperature above absolute zero emits radiation. The hotter the object, the shorter the wavelength of the radiation it produces. A star like the sun emits most of its energy in visible light, the narrow band of wavelengths that human eyes evolved to detect. But cooler objects, planets, moons, clouds of gas and dust, emit their energy at longer wavelengths, in the infrared. You cannot see infrared with your eyes. You can feel it. When you hold your hand near a hot surface without touching it, and sense the warmth radiating outward, there is infrared radiation hitting the nerve endings in your skin. Every warm object around you is glowing in infrared right now. You are glowing in infrared right now. Voyager 2 carried cameras that observed primarily in visible light. At Uranus, those cameras recorded what the planet looked like in the same wavelengths your eyes would detect if you were floating beside the spacecraft and staring out the window. The problem is that Uranus, at its distance from the sun, and with its methane-rich upper atmosphere, does not give visible light cameras very much to work with. Methane absorbs red wavelengths and reflects blue-green, producing that smooth, uniform color. Beneath the methane haze, cloud structures and atmospheric features exist, but they are hidden from visible light observation, the way objects behind frosted glass are hidden from someone trying to read a book on the other side. You can see the general shape, you can detect that something is there, but the detail is gone. Webb does not look through frosted glass. Webb looks in wavelengths where the glass is transparent. The James Webb Space Telescope orbits the sun at a point called Lagrange Point 2, roughly 1.5 million kilometers from Earth, on the side opposite the sun. Its primary mirror is 6.5 meters across, composed of 18 gold-coated hexagonal segments. And its instruments are cooled to temperatures below minus 230 degrees Celsius. That extreme cold is essential because the telescope itself would otherwise glow in infrared, blinding its own detectors with thermal noise. Webb has to be colder than the things it is trying to observe. And at minus 230 degrees, the telescope carries 4 science instruments. For Uranus, the 2 most important are the near-infrared camera and the near-infrared spectrograph. The near-infrared camera captures images in wavelengths ranging from roughly 0.6 to 5 microns, spanning from the edge of visible red light deep into the near-infrared. The near-infrared spectrograph splits incoming light into its component wavelengths, the way a prism splits white light into a rainbow, allowing scientists to identify the chemical fingerprints of specific molecules and measure temperatures at different altitudes in a planet's atmosphere. The difference between what Voyager saw and what Webb sees is not like upgrading from a standard television to a high-definition one. It is like switching from a black and white security camera pointed at the outside of a building to a thermal imaging system that can see through the walls. The information is categorically different. Voyager showed us what Uranus looks like. Webb shows us what Uranus is doing. The first Webb observation of Uranus was released to the public in April of 2023. Even within the scientific community, the reaction was immediate and visceral. The image, a 12-minute exposure using just 2 infrared filters, revealed a planet that bore almost no resemblance to the Voyager photograph that had defined Uranus for 4 decades. The rings came first. Not as faint, ambiguous traces requiring extreme image processing, but as sharp, distinct structures encircling the planet in brilliant infrared clarity. Uranus has 13 known rings, and 11 of them were visible in that single Webb image. Some were so bright at infrared wavelengths that where they passed close to each other, they appeared to merge into broader bands. The outermost ring, called the Epsilon ring, was the most prominent. But the image also captured the inner rings and, critically, the Zeta ring. The Zeta ring is the closest ring to the planet and the faintest of all. It is so diffuse, so dim, that only 2 other observation platforms had ever detected it. Voyager 2 glimpsed it during the 1986 flyby. The Keck Observatory in Hawaii resolved it using adaptive optics decades later. Webb captured it in 12 minutes. That detail alone tells you something about the leap in capability. A ring that required the most powerful ground-based telescope in the world and advanced atmospheric correction technology to barely detect was casually visible in a brief Webb exposure alongside 11 other rings, 14 moons, and background galaxies billions of light years away, scattered across the same field of view. The ring structures themselves carried scientific information that Voyager's brief flyby could only hint at. Uranus has 13 known rings, and the character varies dramatically. The outermost and brightest, the Epsilon ring, is narrow and dense, confined by the gravitational influence of 2 small shepherd moons, Cordelia and Ophelia, that orbit on either side of it. Their gravity acts like walls, preventing the ring particles from spreading outward or inward. Without those shepherds, the Epsilon ring would disperse within a few thousand years. The fact that it exists at all tells scientists that the dynamical relationship between the moons and the ring material is actively maintained, not a relic of some ancient configuration. The inner rings are different. They are broader, more diffuse, and composed of darker material. The Zeta ring behaves almost like a sheet of dust, rather than a discrete ring. Webb's ability to resolve it so cleanly in infrared tells researchers something about its composition. Webb's ability to detect it so cleanly in infrared tells researchers something about its composition. The ring particles reflect infrared light differently depending on their size, shape, and surface material. Webb's multi-filter observations allow scientists to begin constraining these properties, building a picture of what the rings are actually made of rather than simply where they are. There is a deeper question lurking in the ring data that Webb has brought into sharper focus. The rings of Uranus may not be ancient. Unlike Saturn's rings, which some models suggest could be billions of years old, the Uranian rings show characteristics that are consistent with a much younger system. The narrow, sharp-edged rings require active gravitational confinement to survive. The dark coloring of the ring particles suggests they have been exposed to radiation and micrometeorite bombardment for a relatively short time, cosmologically speaking. Some researchers have proposed that the current ring system is the debris of a moon, or moons, that were destroyed by collisions within the last few 100 million years. If true, the rings Voyager photographed and Webb is now studying in infrared detail are not a permanent feature of the planet. They are a snapshot of an ongoing process of destruction and reformation. A system where moons break apart, become rings, and eventually reassemble into new moons, cycling between states over timescales of tens to hundreds of millions of years. Webb cannot confirm or rule out this hypothesis on its own, but its detailed imaging of the ring structure, combined with the discovery of new small moons like S2025 U1 embedded within the system, provides the kind of data needed to test it. Every new moonlet found orbiting among the rings is another data point in the gravitational puzzle. Every measurement of ring particle size and composition narrows the range of possible histories. But the rings, as visually striking as they were, told only part of the story. What Webb revealed on the planet's surface was where the real departure from Voyager began. Near the north pole of Uranus, Webb detected a seasonal polar cap. This is a bright region that appears when the pole begins tilting toward the sun, as the planet moves through its 84 Earth-year orbit. Uranus is currently approaching its northern summer solstice, expected in 2028, and the polar cap is growing more prominent as more sunlight reaches the pole. Voyager 2, arriving in 1986, observed the planet during a different seasonal phase and from a different viewing geometry. It saw the South Pole. The polar cap it could detect was far less developed, and under visible light observation, far less detailed. Webb's infrared view of the North Polar Cap showed something Voyager never could have detected. The cap has internal structure. There was a bright, white inner region, and a dark lane surrounding it at lower latitudes, creating a kind of boundary between the brightest part of the cap and the surrounding atmosphere. At the edge of this boundary, bright cloud features appeared, some of them clearly storm systems. A particularly bright cloud was visible on the planet's limb, the edge of the disk as seen from Webb's perspective. These were not the barely there contrast enhancements that the Voyager imaging team had to strain to extract from their data. These were vivid, obvious atmospheric features, unmistakable even at a glance. That first image was a proof of concept. 12 minutes, 2 filters, and it had already overturned 40 years of visual memory. But it was still a limited view, like glancing at a landscape through 2 panes of colored glass. Each filter isolated a narrow range of infrared wavelengths, and what you could learn about the atmosphere depended entirely on which wavelengths you chose. Different molecules absorb and emit at different wavelengths. Different atmospheric altitudes become visible depending on which wavelength you observe. 2 filters gave you 2 slices through the atmosphere. What scientists needed was more slices, more wavelengths, more depth. The December 2023 image delivered exactly that. Webb observed Uranus using 4 separate filters, spanning from roughly 1.4 microns to 4.6 microns, each one sampling a different layer of the atmosphere and a different set of physical processes. The resulting composite image assigned a different color to each filter: blue for the shortest wavelength, cyan, yellow, and orange for progressively longer ones, producing a false color portrait that encoded atmospheric information in its hues. Regions that appeared blue were reflecting short wavelength infrared light from high altitude hazes. Regions that appeared orange were emitting thermal radiation from deeper, warmer layers. The polar cap, the storms, and the rings each appeared in different colors depending on their altitude, temperature, and composition. The effect was transformative. Where the April image had shown a ringed planet with a bright polar cap, the December image showed a structured atmosphere with vertical complexity. The polar cap was not a flat, uniform bright spot. It had layers. The bright inner region sat at a different altitude than the darker lanes surrounding it, and the storm clouds at the cap's edge appeared to be erupting from below the main cloud deck, punching upward into the higher atmosphere where they caught more sunlight and glowed more brightly in the shorter infrared wavelengths. The storms themselves were more numerous than the April image had suggested. Several bright features appeared near and below the southern border of the polar cap, scattered across different longitudes. Their distribution hinted at a connection between the seasonal solar heating at the pole and the atmospheric circulation that was transporting energy and material from one latitude to another. Some of the features were compact and bright, consistent with convective updrafts, columns of gas rising rapidly from deeper layers and condensing at higher altitudes, the way thunderstorm clouds build on Earth. Others were more diffuse, elongated smears that suggested wind shear was stretching them across the disk as the planet's rapid 17-hour rotation pulled at the atmosphere. That rotation posed its own challenge for Webb. Uranus turns fast enough that atmospheric features move visibly during even moderate exposure times. A storm cloud can shift its apparent position on the disk within minutes. The imaging team had to balance exposure length against rotational smearing, taking frames short enough to freeze the motion, but long enough to collect sufficient infrared light from a planet nearly 2 billion miles away. The resulting images were composites, built from separate exposures, carefully aligned and stacked to produce the final portrait. In the wider field of view, the December image captured 14 of the then 27 known moons as tiny blue dots scattered around the ring system. Beyond the moons, the background was peppered with distant galaxies, some appearing as faint orange smudges, others as fuzzy white shapes with discernible structure. Two particularly prominent galaxies appeared to the right of the planet, their light having travelled billions of years to arrive in the same frame as a world orbiting our own sun. The juxtaposition was a quiet reminder of Webb's dual nature. The same instrument that was rewriting the textbook on a planet in our solar system was simultaneously looking through that planet's neighborhood into the deep universe beyond it. That December portrait was the most detailed infrared image of Uranus ever produced. But it was still a single frozen moment. To understand what a planet is doing, you need to watch it over time. And in January of 2025, that is exactly what happened. An international team led by Paola Taranti, a planetary science doctoral student at Northumbria University in England, used Webb's near-infrared spectrograph to monitor Uranus continuously for approximately 15 hours on January 19th, 2025. The observation was part of a general observer program led by Henrik Mellin, also at Northumbria. The spectrograph did not just take pictures, it split the infrared light from Uranus into its spectral components at every point across the planet's disk, creating a three-dimensional dataset that captured the chemical composition, temperature, and density of the upper atmosphere as the planet rotated. Uranus completes one full rotation in roughly 17 hours. 15 hours of continuous observation meant the team watched nearly an entire Uranian day unfold. As the planet turned, different longitudes rotated into and out of view, allowing the spectrograph to build a map of the upper atmosphere that covered a substantial fraction of the planet's surface. The methodology is worth understanding because it illustrates why this observation could not have been done before Webb existed. The near-infrared spectrograph was used in its integral field unit mode, which means it did not just record a single spectrum averaged across the planet's disk. It recorded a spectrum at every spatial point across the field of view simultaneously, creating a data cube. Each slice of that cube corresponds to a different wavelength of infrared light, Each spatial point corresponds to a different location on the planet's surface. By stepping through the wavelengths, the team could identify where specific molecules were emitting light and at what intensity, which in turn revealed the temperature and density of the atmosphere at different altitudes and different longitudes. The key emission they tracked was from a specific molecular ion of hydrogen, a charged molecule that forms in the upper atmosphere when ultraviolet light and energetic particles strip electrons from hydrogen gas. This ion glows faintly in infrared, and its brightness depends on the local temperature and the density of the surrounding gas. By measuring its emission across the planet's disk as Uranus rotated, the team could reconstruct the three-dimensional structure of the ionosphere, the atmospheric layer where these ions concentrate, from roughly 1,000 kilometers above the cloud tops to more than 5,000 kilometers altitude. The result was not a flat map. It was a layered, altitude-resolved portrait showing how the ionosphere varies with longitude and height. The team found that ion densities peaked at roughly 1,000 kilometers above the clouds, while temperatures reached their highest values between 3,000 and 4,000 kilometers. The distribution was not uniform. Some longitude ranges showed enhanced emission extending to higher altitudes, while others showed the ionosphere sitting lower and dimmer. These variations track the wobbling geometry of the magnetic field, confirming that the planet's lopsided magnetic structure directly shapes the vertical extent of its atmosphere. No previous observation had achieved anything close to this level of structural detail. Ground-based telescopes could measure a disk average temperature, a single number representing the entire visible hemisphere. Voyager's instruments could sample the atmosphere along a single trajectory during the flyby. Webb, sitting 1.5 million kilometers from Earth, produced a full three-dimensional atmospheric map over a near-complete rotation. The distance was a disadvantage for spatial resolution, but an advantage for temporal coverage. Webb could watch the entire visible hemisphere rotate past, something an orbiting spacecraft could only do from one vantage point at a time. What that map revealed was the first three-dimensional view of Uranus's upper atmosphere ever constructed. And it was not the uniform, featureless envelope that 4 decades of post-Voyager assumptions had led scientists to expect. The charged molecules that make up Uranus's ionosphere, the upper atmospheric layer where atoms are stripped of electrons by solar radiation and particle bombardment, were distributed unevenly across the planet. In some regions, the ionosphere extended higher, reaching altitudes of roughly 5,000 kilometers above the cloud tops. In other regions, it sat lower, compressed toward the surface. This uneven distribution was not random. It followed a pattern shaped by the planet's magnetic field. The same wildly tilted, offset magnetic field that Voyager had detected in 1986, but couldn't study in any spatial detail. And within this uneven ionosphere, Webb detected auroras. Auroras on Earth are the northern and southern lights, curtains and ribbons of glowing gas produced when charged particles from the solar wind are funneled along magnetic field lines into the upper atmosphere near the poles. They form relatively neat ovals around Earth's magnetic poles, because Earth's magnetic field is roughly aligned with its rotational axis. The field lines converge at the poles in an orderly pattern, and the auroras follow. Uranus does not work that way. Its magnetic field is tilted nearly 60 degrees from the rotational axis and displaced from the center of the planet. This means the magnetic poles do not sit anywhere near the geographic poles. As Uranus rotates, the magnetic field wobbles dramatically, sweeping the magnetic poles across the planet's surface in complex, looping paths. Charged particles entering the magnetosphere do not get funneled into neat polar rings. They get scattered into irregular, shifting patterns that trace the chaotic geometry of the offset field. Webb's spectrograph detected these auroras as regions of enhanced infrared emission, appearing in the data as rosy, glowing patches spread across the planet's disk. They were not concentrated at the poles. They were distributed across a range of latitudes, extending from roughly 25 degrees north to 25 degrees south, following the contours of the lopsided magnetic field. As the planet rotated, the auroral regions shifted, brightened, and dimmed in patterns that track the wobble of the magnetic geometry beneath them. Taranti described the finding in clear terms. She noted that Uranus's magnetosphere is one of the strangest in the solar system, because of how tilted and offset it is from the planet's rotation axis, which means the auroras sweep across the surface in complex ways. Webb had now shown how deeply those effects reach into the atmosphere. The observation revealed energy being transported vertically through the upper atmosphere in ways that no previous instrument had resolved. The auroral detection carried a second implication that was less visually dramatic, but scientifically just as significant. The presence, distribution, and intensity of auroras are direct traces of what the magnetosphere is doing. They reveal where charged particles are entering the atmosphere, how much energy is being deposited, and how the magnetic field is structured at the altitudes where the particles interact with atmospheric gases. Webb's 15-hour observation effectively used Uranus's own auroras as a diagnostic tool, mapping the magnetic field's influence on the atmosphere in real time. No spacecraft orbiting the planet could have done this more efficiently from its single vantage point than Webb did from 1.5 million kilometers away from Earth. But the observation also confirms something that nobody can yet explain. Uranus's upper atmosphere is cooling. This trend was first noticed in ground-based observations during the 1990s. Measurements of the planet's ionospheric temperature showed a decline that seemed inconsistent with the energy inputs the planet was receiving. The sun provides energy. Auroral processes deposit energy. Internal heat, however faint, should contribute. Yet the upper atmosphere was getting colder. Webb's 2025 measurements extended that trend into the present. The team reported a column-weighted temperature of approximately 426 kelvins, which is roughly 150 degrees Celsius. That figure is cooler than values reported in earlier ground-based work, and slightly higher than a separate Webb disk average temperature of 415 kelvins. A difference the team attributed to variations in what portion of the atmosphere each measurement technique samples. The key finding was not the exact number, but the direction. After more than 3 decades of observations across multiple platforms, Uranus's upper atmosphere is still cooling, and the rate shows no sign of reversing. To appreciate how strange this is, consider the thermal budgets of the other giant planets. Jupiter receives a substantial amount of energy from the sun, but radiates nearly twice as much as it absorbs. The excess comes from the planet's interior, residual heat left over from its formation 4.5 billion years ago, still slowly leaking outward through the atmosphere. Saturn shows an even larger imbalance, radiating roughly 2.5 times the energy it receives, driven by a combination of primordial heat and an ongoing process called helium rain, where helium droplets condense in the deep atmosphere and fall toward the core, converting gravitational potential energy into thermal energy as they descend. Neptune, despite being the most distant giant planet and receiving the least solar energy, radiates more than 2.5 times what it absorbs. Its internal heat source is vigorous enough to drive wind speeds exceeding 1,000 miles per hour, making Neptune's atmosphere one of the most dynamic in the solar system. Uranus stands alone. It radiates only slightly more energy than it receives from the Sun, possibly as little as 1.06 times its absorbed solar energy. Its internal heat contribution is either negligible or somehow trapped below the atmosphere in a way that prevents it from reaching the upper layers. And the upper atmosphere, rather than being warmed by the faint internal heat or by auroral energy deposition, is actively cooling. The trend has persisted for over 30 years across measurements from Voyager, ground-based observatories, and now Webb. Something about this planet's thermal behavior is fundamentally different from every other giant world we can study, and no existing model explains it. This is deeply unusual. On every other giant planet where upper atmospheric temperature has been measured, the temperature is either stable or higher than what solar heating alone can explain. Jupiter, Saturn, and Neptune all have upper atmospheres that are warmer than models predict based on their distance from the Sun. Scientists have proposed various mechanisms for this extra heat, including gravity wave dissipation, auroral heating, and energy transport from the deep interior. The fact that these mechanisms work on 3 other giant planets but apparently fail at Uranus or are overwhelmed by some unknown cooling process is a genuine mystery. Webb has confirmed the problem exists. It has not solved it. Then, in August of 2025, Webb delivered one more finding that drove home the gap between what Voyager saw and what actually exists at Uranus. A team led by Mariame El Mutamid at the Southwest Research Institute used Webb's near-infrared camera to conduct a series of 10 40-minute-long exposures of the Uranian system. Within that data, they identified a previously unknown moon. Designated S-2025U1, the object is roughly 6 miles across. It orbits close to the main ring system, nestled among the inner moons in a region of complex gravitational interaction. 6 miles. You could walk around this moon in an afternoon. It is so small and so faint that Voyager 2, even during its closest approach, had no chance of detecting it. Ground-based telescopes, even the largest and most powerful, could not find it. Only Webb's extraordinary infrared sensitivity, designed to detect the faintest galaxies in the distant universe, was capable of picking out this tiny speck of reflected light against the glare of the planet and its rings. The discovery brought the total number of known Uranian moons to 29, but the number itself was less important than what it implied. Matthew Tiscarino of the SETI Institute, a member of the discovery team, framed it precisely. He noted that no other planet has as many small inner moons as Uranus, and that their complex interrelationships with the rings hint at a chaotic history that blurs the boundary between a ring system and a system of moons. He added that because the new moon is smaller and much fainter than the smallest of the previously known inner moons, it is likely that even more complexity remains to be discovered. The detection of S-2025U1 also demonstrated something about the limits of every previous observation of the Uranian system. The moon is roughly 6 miles across. At Uranus's distance from Earth, an object that size reflects so little sunlight that it is completely lost in the glare of the planet and rings when observed in visible light, even by the Hubble Space Telescope. Webb's near-infrared camera, designed to detect the faintest galaxies in the early universe at distances of billions of light years, turned that sensitivity inward and found a tiny world hiding among the rings of a planet in our own solar system. The 10 40-minute exposures used to find it were long by Webb standards, each one carefully timed and stacked to build up enough signal to distinguish the moon's faint point of light from the background noise and the scattered light of the rings. The implication is that the Uranian system almost certainly contains additional undiscovered moons below the detection threshold of even this observation. If one 6-mile object was hiding in plain sight, there may be dozens of smaller objects, perhaps only a mile or two across, orbiting among the rings and interacting gravitationally with the ring particles. Each one would be a piece of the dynamical puzzle that governs the ring system's structure and evolution. Each one would be invisible to every telescope currently operating until someone designs an observation specifically to find it. The system is not fully catalogued. It may not be fully catalogable with current technology. That last phrase is the one that matters. Even more complexity remains to be discovered. Every time Webb looks at Uranus with greater sensitivity or longer exposures, it finds something new. Rings that were invisible become visible. Storms that were undetectable become obvious. Auroras that were unknown become mappable. Moons that did not exist in any catalogue appear from the darkness. The system is not empty. It is not quiet. It is not featureless. It has been all of those things only in the images we were capable of taking. Webb did not discover a new Uranus. It revealed the Uranus that was always there. And this raises a question that the images alone cannot answer. The rings, the storms, the auroras, the moons, the cooling atmosphere, none of these features exist in isolation. They are all consequences of something deeper, something structural about this planet that makes it unlike anything else in the solar system. A property so extreme that it warps every aspect of the system built around it. Uranus is tilted. Not slightly, the way Earth is tilted at 23.5 degrees. Enough to give us seasons, but not enough to fundamentally alter how the planet interacts with its star. Uranus is tilted at 98 degrees. Its rotational axis lies almost flat in the plane of its orbit. It does not spin like a top. It rolls like a ball knocked on its side. And every single strange thing Webb has detected, the polar cap, the lopsided auroras, the chaotic magnetic field, the extreme seasons, the bizarre thermal behavior, traces back to that tilt. The question of how a planet gets knocked onto its side, what that does to its magnetic field, its atmosphere, its moons and its rings, and why the consequences are only now becoming visible after 4 decades of near total scientific neglect, is where this story turns from impressive telescope images into something genuinely unsettling. Because the tilt is not just a quirk, it is a scar. And the system it created is stranger than anything Voyager was equipped to see, or any textbook was prepared to describe. Every planet in the solar system spins. Every planet is tilted, at least slightly, relative to the flat plane in which it orbits the Sun. Earth tilts at 23.5 degrees. Mars at roughly 25 degrees. Saturn at about 27. These modest tilts are what give those worlds their seasons. The axis points in a roughly constant direction as the planet orbits. So for part of the year, one hemisphere leans toward the Sun and receives more direct light. creating summer, while the other hemisphere leans away, creating winter. The cycle repeats. The seasons are moderate. The variations are survivable. Life on Earth, in fact, depends on them. Uranus tilts at 98 degrees. That number needs a moment to settle because it changes everything. A tilt of 98 degrees means the planet's rotational axis does not point roughly up and down relative to its orbital plane. It points almost sideways. Uranus does not spin like a top standing upright on a table. It rolls along its orbital path like a ball that has been knocked over and is now tumbling forward. The axis of rotation lies nearly flat in the plane of the orbit, meaning that at certain points in the planet's year, one pole faces the sun, almost directly, while the other points into the blackness of deep space. The question of how this happened has occupied planetary scientists for decades, and the leading answer is violent. The most widely accepted hypothesis is the giant impact theory. Early in the solar system's history, roughly 4 billion years ago, during the chaotic period when the planets were still settling into their final orbits, a protoplanetary body roughly the size of Earth collided with the young Uranus. The impact delivered enough angular momentum to knock the planet's rotational axis from a near vertical orientation to its current sideways position. Computer simulations of this collision have been run by multiple research groups. The models suggest the impactor struck at a glancing angle rather than head-on, transferring angular momentum efficiently to the planet's spin without completely destroying it. Some simulations produce a single catastrophic impact. Others suggest that two or more smaller impacts occurring within a relatively short window could have achieved the same result, gradually tipping the planet over through successive blows. A more recent alternative hypothesis, published in Astronomy and Astrophysics by Melaine Seilenfest and colleagues, proposed that the tilt could have been caused not by a collision, but by a migrating moon. The idea draws on a mechanism already studied for Jupiter and Saturn, where the gradual outward drift of a large moon can, through gravitational resonance, slowly increase the tilt of the host planet's axis. Seilenfest's team ran simulations showing that a hypothetical Uranian moon with at least half the mass of Earth's moon migrating outward at a rate of 6 centimeters or more per year could have tipped Uranus to nearly 90 degrees over hundreds of millions of years. At a tilt of roughly 80 degrees, the moon's orbit would have become unstable, leading to a collision with the planet that locked the axis in its current orientation. This hypothesis is elegant because it explains the tilt without requiring a random, catastrophic impact, and produces the final axis position as a natural dynamical outcome rather than a coincidence of impact geometry. However, it has not been confirmed and remains less widely accepted than the giant impact model. Both hypotheses make predictions about the internal structure of Uranus and the properties of its moon system that a future orbiter mission could test. For now, the cause of the tilt remains one of the oldest unresolved questions in solar system science. Regardless of how it happened, the consequences are what matter for this story, and every consequence flows outward from the same geometric fact. No other major planet behaves this way. Venus rotates backward, which is its own oddity, but its axis is nearly perpendicular to its orbit. Uranus is the only planet in the solar system that orbits on its side. And the consequences of this single geometric fact cascade through every aspect of the planet's behavior, from its seasons to its magnetic field, to the orbits of its moons, to the structure of its rings, to the auroras, Webb detected glowing across its atmosphere. Start with the seasons. Uranus orbits the Sun once every 84 Earth years. That orbit, combined with the extreme tilt, produces the most dramatic seasonal cycle of any planet we know. For roughly 21 Earth years, the North Pole faces the Sun continuously. The Northern Hemisphere is bathed in perpetual daylight, while the Southern Hemisphere sits in total, unbroken darkness. Then, as the planet moves along its orbit, the geometry shifts. The equatorial region begins to face the Sun, and both hemispheres experience something closer to a normal day-night cycle, with the planet's 17-hour rotation creating relatively rapid alternation between sunlight and darkness. Then, the South Pole swings toward the Sun, and the cycle reverses. 21 years of continuous light for the South, 21 years of continuous darkness for the North. These are not subtle seasons. On Earth, the difference between summer and winter is a matter of degree, a tilt of 23.5 degrees, producing longer or shorter days and more or less direct sunlight. On Uranus, the difference between summer and winter at the poles is the difference between perpetual noon and perpetual midnight, sustained for more than 2 decades at a stretch. The energy budget of each hemisphere undergoes a complete inversion over the course of a single Uranian year. One half of the planet is absorbing solar radiation non-stop, while the other half radiates heat into space with no replenishment at all. This should produce extraordinary atmospheric effects. And it does, but not in the ways scientists initially expected. When Voyager 2 arrived in 1986, Uranus was near its southern summer solstice. The South Pole was pointed almost directly at the Sun. Under those conditions, with one hemisphere receiving maximum solar input, models predicted that the sunlit pole would be significantly warmer than the dark equatorial and northern regions. The temperature difference should have driven vigorous atmospheric circulation, visible storms, strong wind patterns, and measurable thermal contrast between the two hemispheres. Voyager found almost none of that. The atmosphere appeared calm. The temperature difference between the sunlit South Pole and the dark equator was surprisingly small. The planet seemed to be distributing heat far more efficiently than models predicted, smoothing out the extreme seasonal forcing into something bland and uniform. This fed directly into the narrative that Uranus was boring. Even its extreme tilt, which should have produced wild atmospheric behavior, appeared to result in nothing more than a quiet, well-mixed atmosphere with no personality. But ground-based observations in the decades following the flyby told a different story. As Uranus moved through its orbit, passing its equinox in 2007 and heading toward its northern summer solstice, the atmosphere began to change. Storms appeared. Bright cloud features developed. Atmospheric activity increased, particularly in the northern hemisphere as it emerged from decades of darkness and began receiving sunlight for the first time in over 20 years. The planet was waking up. The assumption that Uranus was perpetually calm had been based on observing it during a single seasonal phase. As the seasons changed, the atmosphere responded, and it responded dramatically. This is part of what makes Webb's observations so valuable. The telescope is watching Uranus during a different seasonal window than Voyager did. The north polar cap that Webb has imaged in such detail is a seasonal feature, appearing as the North Pole swings toward the Sun, and growing more prominent as solstice approaches in 2028. Scientists do not fully understand the mechanism that produces the polar cap. It appears to involve changes in atmospheric chemistry or cloud formation triggered by increased solar ultraviolet radiation at the pole, but the exact process remains uncertain. What Webb can do, and what no previous instrument could do at this level of detail, is track the cap's evolution over time, watching how it brightens, how its internal structure changes, and how the surrounding atmospheric features respond as the solstice draws closer. The approach to solstice is itself a rare scientific opportunity. The last time Uranus's North Pole was pointed this directly at the Sun was in the 1940s, decades before any telescope existed that could study the planet in infrared. Astronomers alive today will not see this geometry again in their lifetimes. Webb is the first instrument with the sensitivity and wavelength coverage to observe a Uranian solstice in real detail, and the data it collects over the next few years will be the only dataset of its kind for another 84 years. But the seasons are only the first layer of strangeness that the tilt produces. The second is the magnetic field, and the magnetic field is where Uranus crosses the line from unusual into genuinely disturbing. Every giant planet in the solar system has a magnetic field generated by electrically conducting fluid in its interior. For Jupiter and Saturn, that fluid is metallic hydrogen, compressed under such extreme pressure that it behaves like a liquid metal and conducts electricity. The resulting magnetic fields are powerful, roughly aligned with each planet's rotational axis, and centered approximately at the planet's core. Earth's magnetic field follows the same general pattern, generated by convection in the liquid iron outer core and roughly aligned with the spin axis. Tilted by only about 11 degrees, Uranus breaks the pattern completely. The magnetic field measurements that Voyager returned were strange enough as raw numbers, but to understand what they actually mean for the planet as a physical system, you need to picture what a 59-degree tilt and a 1/3 radius offset look like in practice. The magnetic axis does not pass through the core. The magnetic poles do not sit anywhere near the geographic poles, and as the planet rotates, the entire magnetic structure wobbles with it. The result is a magnetosphere unlike anything else in the solar system. On Earth, the magnetic field creates a relatively symmetrical bubble around the planet, with the magnetic poles sitting near the geographic poles. Solar wind particles entering the magnetosphere are funneled along field lines that converge neatly at the polar regions, producing auroral ovals that encircle the poles in predictable, stable patterns. The system is orderly, it is comprehensible. On Uranus, the magnetosphere is a warped, lopsided, constantly shifting structure. As the planet rotates every 17 hours, the tilted, offset magnetic field wobbles dramatically. The magnetic poles sweep across the surface of the planet in looping paths that cover a wide range of latitudes. Imagine a gyroscope with a bent shaft spinning on a tabletop. The wobble is not subtle. It is violent, asymmetric, and constantly changing the orientation of the magnetic field relative to the incoming solar wind. This produces what researchers have described as the most asymmetric auroras in the solar system. Webb's 2025 observations confirm this directly. The auroras detected by the near-infrared spectrograph were not confined to neat rings around the poles. They were spread across the planet's disk, appearing and disappearing as the magnetic field rotated, tracing the chaotic geometry of the offset field through the upper atmosphere. The effect is like someone waving a flashlight in unpredictable arcs through a dark room. The light hits the walls in different places at different times, and the pattern never quite repeats. The tilted, offset magnetic field has a further consequence that scientists are only beginning to appreciate. It means the magnetosphere interacts with the solar wind in a fundamentally different way than any other planets. On Earth, the magnetic axis is roughly parallel to the rotational axis, which means the magnetosphere presents a relatively stable face to the solar wind. On Uranus, because the magnetic axis is tilted so severely relative to both the rotational axis and the orbital plane, the magnetosphere's orientation relative to the solar wind changes drastically as the planet rotates. Every 17 hours, the magnetosphere effectively flips and twists, presenting a completely different geometry to the incoming charged particles. This is part of what made the Voyager 2 flyby data so misleading. The spacecraft passed through the magnetosphere during a brief window when, as the 2024 study by Yasinski showed, the entire system was compressed by an unusual solar wind surge. But even without that compression, the magnetosphere Voyager encountered would have been a snapshot of a single rotational phase, a single orientation of the wobbling magnetic field relative to the solar wind at a single moment. 5.5 hours later, the field would have rotated into a completely different configuration. Voyager captured one frame of a constantly moving picture, and scientists treated it as a still photograph for 40 years. The source of the magnetic field's strange geometry is itself a subject of active research. On Earth and the other giant planets, the magnetic field is generated deep in the interior, in the planet's core, or in the metallic hydrogen layer surrounding it. The field appears to originate not deep in the core, but in the superionic layer between the core and the outer atmosphere. A shallow conducting shell whose off-center geometry naturally produces the displaced, tilted field Voyager detected. Why the field is also tilted so severely is less clear. One hypothesis connects it to the same catastrophic event that produced the axial tilt itself. Something struck Uranus early in its history, likely a protoplanet roughly the mass of Earth, hitting with enough force to knock the planet onto its side. That impact would have disrupted the interior, potentially altering the convection patterns in the conducting fluid layer and establishing the conditions that produce the current tilted, offset field. Neptune's magnetic field shows a similar, though less extreme, tilt and offset, which some researchers argue weakens the impact hypothesis since it would require a similar collision to have struck Neptune as well. Others suggest that the unusual field geometry may simply be a natural consequence of how magnetic fields are generated in ice giant interiors, where the conducting layer is thinner and shallower than in gas giants. Neptune strengthens this argument. When Voyager 2 reached Neptune in 1989, 3 years after the Uranus flyby, it discovered that Neptune's magnetic field was also tilted and offset, though by somewhat different amounts. Neptune's magnetic axis is tilted roughly 47 degrees from its rotational axis and offset from the planet's center by more than half the planet's radius. The geometry is not identical to Uranus's, but the pattern is unmistakable. Both ice giants have magnetic fields that are dramatically misaligned with their spin axes and displaced far from their centers. Both are radically different from the neat, centered, axis-aligned fields of Earth, Jupiter, and Saturn. The fact that two planets with similar sizes, similar compositions, and similar internal structures both produce this kind of anomalous magnetic geometry makes it difficult to attribute the phenomenon to a one-time accident like a giant impact. If the tilt were caused solely by the collision that knocked Uranus on its side, Neptune would need its own separate explanation, and no compelling candidate exists. The more parsimonious conclusion, and the one gaining traction in the planetary science community, is that tilted, offset magnetic fields are simply what ice giant interiors produce. The thin, shallow conducting shell of superionic material generates a field with a fundamentally different geometry than the deep metallic hydrogen dynamos inside Jupiter and Saturn. Regardless of the cause, the consequences are observable, and Webb is observing them for the first time with the sensitivity needed to trace them through the atmosphere. Now extend the tilt downward, from the planet to its moons. Uranus has 29 known moons. The 5 largest, Miranda, Ariel, Umbriel, Titania, and Oberon, were discovered between 1787 and 1948, long before the space age began. All 5 orbit in the planet's equatorial plane. Because Uranus is tilted at 98 degrees, the moon's orbits are tilted at 98 degrees relative to the solar system's orbital plane. They circle the planet in orbits that are nearly perpendicular to the path Uranus follows around the sun. This means the moons share the planet's extreme seasonal cycle. As the north pole of Uranus faces the sun, the north poles of the moons do as well. The entire system, planet, rings, and moons, is tilted together, locked into the same sideways orientation by gravity. Voyager 2 flew past the 5 major moons during its brief encounter and returned the only close-up images that exist of any of them. What it saw was unexpectedly varied. Miranda, the smallest and innermost of the 5, showed some of the most bizarre surface geology in the solar system. Its surface is a patchwork of different terrains, including massive trapezoidal formations called coronae, regions of grooved, ridged terrain that appear to have been formed by internal geological activity. Ariel showed extensive rift canyons and faulting, suggesting that its surface had been reshaped by tectonic forces relatively recently in geological terms. Even the outer moons, Titania and Oberon, showed evidence of past geological activity, with fault systems and surface features that hinted at internal heating. Miranda, the smallest of the 5, was the source of the greatest bewilderment. Its surface looked like nothing else in the solar system. 3 massive formations called coronae dominated the hemisphere Voyager imaged, each one a roughly trapezoidal region of grooved, ridged terrain, sharply bounded by the smoother, more heavily cratered surface surrounding it. The coronae looked almost like puzzle pieces that had been pressed into the surface from below, their parallel ridges and valleys suggesting enormous forces had stretched and compressed the crust. Near one of them, called Inverness Corona, a towering scarp known as Verona Rupes was initially estimated at roughly 12 miles high, which would have made it one of the tallest cliff faces in the solar system. Later reanalysis by planetary scientist Paul Schenck revised that figure significantly downward to approximately 3 miles, though the exact height remains uncertain due to the limited resolution of the Voyager images. Even at the lower estimate, the feature is a dramatic fracture in the surface of a world only 290 miles across. Ariel's surface was different but equally striking. Broad rift valleys cut across the moon's surface, some of them hundreds of miles long and more than 6 miles deep. The floors of these valleys were smooth, suggesting they had been flooded by material erupting from below, a process called cryovolcanism, where the erupting material is not molten rock, but liquid water, ammonia, or other volatile compounds that freeze upon reaching the surface. The rifts indicated that Ariel's crust had been pulled apart by extensional forces, the kind of stress produced when a warm, expanding interior pushes outward against a cold, rigid shell. Titania, the largest Uranian moon, showed a network of enormous fault scarps crossing its surface, the longest extending for nearly 1,000 miles across the icy terrain. These faults indicated that the moon's interior had cooled and contracted at some point in its history, shrinking slightly and causing the rigid crust to crack under compression. Oberon, the outermost of the five, was the most heavily cratered and appeared the least geologically active, but even its surface showed hints of dark material on the floors of some craters, possibly cryovolcanic deposits that had seeped upward through fractures in the ice. The largest of these dark-floored craters, Hamlet, spans roughly 120 miles across. The material filling its floor is distinctly darker than the surrounding ice, and its smooth texture suggests it was deposited as a fluid that solidified after reaching the surface. Each moon told a piece of the same story. Something had heated these worlds from the inside, driving geological processes that reshaped their surfaces long after they should have cooled into inert ice balls. At the time, these observations were surprising but not fully understood. The Voyager team noted the evidence of geological activity but lacked the data to determine what could have driven it. The moons are small. Miranda has a radius of only 146 miles, smaller than the distance between London and Paris. Objects that small should cool quickly, losing their internal heat to space and becoming geologically dead within the first billion years of the solar system's history. And yet, their surfaces told a different story. In the decades since Voyager, the evidence has mounted that several of Uranus's moons may harbor, or may have recently harbored, subsurface oceans. Liquid water beneath icy crusts. The same phenomenon that makes Jupiter's moon Europa and Saturn's moon Enceladus such compelling targets for astrobiology. In 2024, a study published in the Planetary Science Journal by Caleb Strom and colleagues examined Miranda's surface features in detail using the Voyager images and computational stress modeling. They mapped the cracks, ridges, and coronae across the moon's surface, then ran simulations of different possible internal structures to determine which configurations would produce the observed surface patterns. The result pointed clearly toward a subsurface ocean. The stress patterns that best match Miranda's surface required a liquid water layer at least 100 kilometers deep, hidden beneath an icy crust no more than 30 kilometers thick. Given Miranda's tiny radius, that ocean would have occupied nearly half the moon's total volume. The finding was described by co-author Tom Nordheim of Johns Hopkins Applied Physics Laboratory as incredibly surprising. Finding evidence of an ocean inside a small object like Miranda challenges fundamental assumptions about how internal heating works in small, icy bodies. A follow-up study published in 2026 in the journal Icarus applied the same methodology to Ariel. The results were similar. Ariel's surface features, the rift canyons, the faulting, the evidence of resurfacing were best explained by a subsurface ocean roughly 170 kilometers deep, making up approximately 55% of the moon's total volume, existing as recently as 1 billion years ago. And Webb added another thread. In 2024, observations of Ariel using the James Webb Space Telescope detected surface deposits of carbon dioxide ice. Spectral analysis suggested the carbon dioxide was not being delivered from external sources like micrometeorite bombardment. It appeared to be coming from the moon's interior. The concentrations were striking. Ariel's carbon dioxide ice deposits are among the most abundant found on any moon in the solar system, far exceeding what external sources like micrometeorite bombardment or charged particle interactions with surface ice could plausibly deliver. More telling still, Webb's spectral analysis detected signatures consistent with carbonate minerals, a class of salts that form specifically when rock interacts with liquid water. Carbonates do not appear spontaneously on an airless, frozen surface. Their presence points toward chemistry happening below the crust, where warm water meets a rocky interior, exactly the conditions a subsurface ocean would provide. Richard Cartwright of the Johns Hopkins Applied Physics Laboratory concluded that a subsurface ocean might be actively replenishing aerial surface deposits of carbon dioxide, implying that the ocean may not be a relic of the past, but a feature of the present. Broader thermal modeling studies have extended the possibility further. Research published in 2023 by Julie Castillo-Rogers and colleagues found that plausible thermal evolution scenarios for the larger Uranian moons, Ariel, Umbriel, Titania, and Oberon, could all support the existence of liquid water oceans beneath their surfaces at the present day. The heating sources include residual radioactive decay in each moon's rocky core and tidal heating generated by gravitational interactions between the moons as they orbit Uranus. The tidal heating is particularly relevant because the orbital resonances between the inner moons, the gravitational push and pull as they lap each other in their orbits, can flex their interiors enough to generate significant heat, the same mechanism that keeps Europa's ocean liquid at Jupiter. The mechanism works like this. When two moons orbit the same planet in orbits whose periods form a simple ratio, they pass each other at regular intervals. Each time they align, the gravitational tug between them is strongest at the same point in their orbits. This repeated tug pulls the inner moon's orbit slightly out of round, making it more elliptical. As the moon follows that elliptical path, it moves closer to and farther from Uranus with every orbit. The changing gravitational pull from the planet flexes the moon's interior, the way repeatedly bending a paperclip heats the metal at the bend. That flexing generates friction, and friction generates heat. For Miranda and Ariel, the orbital resonances are believed to have been stronger in the past than they are today. The moons have since drifted apart slightly, weakening the resonance and reducing the tidal heating. But the geological evidence on their surfaces records the period when the heating was intense enough to maintain liquid water beneath the ice. And the Webb detection of carbon dioxide on Ariel's surface, apparently replenished from below, suggests the story may not be entirely in the past. This means the Uranian system is not just a tilted planet with some rings and a few inert moons. It is potentially a system of ocean worlds, small icy bodies with liquid water interiors, orbiting a planet whose extreme tilt and offset magnetic field create an environment without parallel among the known planets, and all of it was invisible to Voyager. The spacecraft could not detect subsurface oceans. It could not analyze surface chemistry in the infrared. It could not monitor the moons over time to track changes. It saw surfaces, took photographs, and moved on. The rings add yet another dimension to this picture. Webb's detection of the 29th moon, S2025 U1, orbiting close to the main ring system, highlighted something that planetary scientists have been increasingly recognizing about the Uranian rings. They are not a separate system from the moons. They are intertwined. The inner moons of Uranus orbit within and among the rings in a complex gravitational dance. The moons shepherd the rings, their gravity confining ring particles into narrow bands and clearing gaps between them. But the relationship is not stable. It is dynamic, evolving, and in some cases, chaotic. The small inner moons interact with each other gravitationally, trading angular momentum in ways that can shift their orbits over timescales of thousands to millions of years. Some researchers believe the current ring system may not be ancient. It may be the debris of past collisions between small moons, a system that is constantly being destroyed and reformed as the gravitational interactions between moons lead to occasional catastrophic impacts. Tiscarino's observation that the Uranian system blurs the boundary between a ring system and a system of moons captures this perfectly. The rings and the moons are not distinct categories at Uranus. They are a continuum, a spectrum of objects ranging from microscopic dust particles to 6-mile-wide moonlets to 100-mile-wide worlds with possible internal oceans, all orbiting in the same tilted plane, all governed by the same gravitational dynamics, all shaped by the same extreme geometry that makes Uranus unlike anything else we know. And every piece of this system, every ring particle, every moonlet, every aurora, every storm cloud, every molecule in the cooling upper atmosphere exists in a state that is currently changing. The planet is approaching solstice, the polar cap is brightening, the seasons are shifting, the atmosphere is evolving, and we are watching it happen for the first time with instruments capable of seeing what is actually there rather than what our limited tools could show us 4 decades ago. The gap between what we thought we knew and what we are now learning is not a gap in detail. It is a gap in kind. Voyager showed us a quiet planet. Webb is showing us a complex, active, layered system with storms, auroras, possible ocean moons, chaotic ring dynamics, and a magnetic field so distorted it rewrites the rules of magnetospheric physics. These are not incremental updates to the old picture. They are a demolition of it. The featureless blue marble never existed. It was a product of visible light cameras, a 5.5-hour visit, a solar wind anomaly, and 40 years of looking elsewhere. The real Uranus was always there, tilted on its side, rolling through its 84-year orbit, cycling through its impossible seasons, wrapped in a magnetic field that wobbles and warps with every rotation, surrounded by moons that may contain more liquid water than anyone imagined, threaded through with rings that blur the line between debris and satellites. And we missed all of it. Not because the evidence was hidden by some cosmic conspiracy. Not because the universe was keeping secrets. But because we pointed one spacecraft at it for a few hours during a freak event, took a photograph that happened to look boring, and decided that was enough. What that failure of attention means, not just for Uranus, but for how we understand every planet we have not yet studied carefully, is the final and most unsettling part of this story. There is a document that sits at the center of American planetary science planning. It is called the Planetary Science and Astrobiology Decadal Survey, and it is produced roughly once every 10 years by the National Academies of Sciences, Engineering, and Medicine. The document represents the consensus of the planetary science community on what missions should be prioritized for the coming decade. It is not a wish list. It is a strategic blueprint that shapes billions of dollars in funding decisions, guides the development of spacecraft that will not launch for years or decades, and determines which worlds in the solar system will receive the next wave of human attention. In the 2023 to 2032 survey, released in April of 2022, the top priority flagship mission was not a return to Mars. It was not a probe to the moons of Jupiter or Saturn. It was a Uranus orbiter and probe. That recommendation was extraordinary. Uranus had never been the top priority in any previous decadal survey. It had lingered for decades at the edges of the conversation, acknowledged as scientifically interesting but perpetually deprioritized in favor of targets that seemed more urgent, more visually compelling, or better understood. Mars received rover after rover. Jupiter's moon Europa earned a dedicated mission, the Europa Clipper, which launched in 2024. Saturn's system was explored for 13 years by Cassini. Meanwhile, Uranus sat in the outer dark, studied from Earth through ground-based telescopes and, increasingly, through Webb, but with no dedicated spacecraft even in development. The Decadal survey changed that. The science community looked at the accumulated evidence, weighed the gaps in knowledge, and concluded that the single most important place to send a flagship mission in the coming decade was the planet that had been ignored the longest. The reasoning was not sentimental, it was scientific, and it rested on a realization that has been building quietly for years. Uranus-sized planets are probably the most common type of planet in the galaxy. This is not speculation, it's an observational finding. Over the past 2 decades, space telescopes like Kepler and the Transiting Exoplanet Survey satellite have discovered thousands of planets orbiting other stars. When astronomers began sorting those planets by size, a striking pattern emerged. The most common category was not gas giants like Jupiter and Saturn. It was not rocky worlds like Earth and Mars. It was planets roughly 2 to 4 times the radius of Earth. A size range that corresponds almost exactly to Uranus and Neptune. These worlds, often called sub-Neptunes or mini-Neptunes, appear in planetary system after planetary system around stars throughout the Milky Way. Current estimates suggest there may be billions of them in our galaxy alone. They are the default outcome of planet formation, the most typical kind of world the universe produces, and we understand them less than almost any other category of planet. The reason is simple. The only examples we can study up close are Uranus and Neptune. Every other sub-Neptune in the catalogue is dozens or hundreds of light years away, visible only as a slight dimming of starlight when it passes in front of its host star, or as a faint wobble in the star's motion, caused by the planet's gravitational pull. We can measure their sizes, we can estimate their masses. In some cases, Webb can even detect molecules in their atmospheres. But we cannot study their internal structure, their magnetic fields, their ring systems, their moons, or their weather in any detail. For that, we need a nearby example. We have exactly 2, and one of them, Uranus, has been visited once for 5.5 hours during a solar storm by a spacecraft that was not designed to study it. This means our ignorance of Uranus is not just ignorance of one planet, it is ignorance of the most common type of planet that exists. Every assumption we make about how sub-Neptunes work, how they form their atmospheres, how they generate their magnetic fields, how they retain or lose heat, how their moons and rings behave, rests on a foundation that is almost entirely theoretical, because the observational foundation barely exists. Webb has begun to change this. The infrared observations of Uranus's atmosphere, rings, auroras, and moons are providing data points that modelers can use to test their theories. But Webb is 1.5 million kilometers from Earth, nearly 2 billion miles from Uranus. It can see the planet as a small disk, resolve its largest features, and detect the chemical signatures in its atmosphere. It cannot measure the deep interior. It cannot sample the composition of the rings. It cannot fly through the magnetosphere and map it from the inside. It cannot orbit the moons and look for plumes of water vapor erupting from subsurface oceans. For all of that, you need to go there. The proposed Uranus orbiter and probe would do what Voyager 2 could not. It would enter orbit around Uranus, spending years rather than hours in the system. It would release a probe into the atmosphere, descending through the cloud layers and measuring composition, temperature, pressure, and wind speed at every altitude. It would conduct close flybys of the major moons, mapping their surfaces in high resolution, measuring their gravitational fields to determine whether liquid water layers exist beneath their ice, and searching for signs of geological activity. It would map the magnetic field from inside the magnetosphere across multiple rotations, building the three-dimensional picture that Voyager's single pass could never provide. And it would study the rings at close range, determining their composition, age, and the gravitational dynamics that maintain them. The mission, if funded and launched on the timelines discussed in the Decadal Survey, would arrive at Uranus in the early to mid-2040s. That timeline is not accidental. It is driven partly by orbital mechanics, the alignment of planets and the availability of gravity assists, and partly by the approaching solstice. If the spacecraft arrives while the North Pole is still strongly illuminated, it will be able to study the polar cap, these seasonal atmospheric changes, and the illumination-driven chemistry that Webb has begun to document from afar. Miss the window, and those observations will not be possible again for another 84 years. But as of right now, the Uranus orbiter and probe is a recommendation, not a funded program. It exists as a priority on paper, endorsed by the scientific community, but not yet approved for development by NASA. The history of planetary science is littered with recommended missions that were delayed, descoped, or cancelled as budgets shifted and political priorities changed. The Uranus mission has strong scientific backing, but it does not yet have the political and financial commitment needed to move from concept to construction. This means that for the foreseeable future, Webb remains the best tool humanity has for studying Uranus. And Webb has already revealed enough to make clear that the planet we thought we knew was a fiction. Consider the cooling mystery. Uranus's upper atmosphere has been losing temperature since at least the early 1990s. Webb's 2025 measurements confirmed the trend is continuing. The temperature the team recorded was not just lower than previous measurements from other instruments. It was dramatically lower than what models predict based on the energy the planet receives from the sun and from its own auroral processes. This is not a minor discrepancy. On every other giant planet, the upper atmosphere is warmer than solar heating alone can explain. Jupiter, Saturn, and Neptune all show excess temperatures that scientists attribute to energy being transported upward from the interior or deposited by auroral and magnetospheric processes. The mechanisms are still debated, but the direction is consistent. The upper atmospheres are too warm, and the challenge is explaining where the extra heat comes from. At Uranus, the problem is inverted. The upper atmosphere is too cold, and it is getting colder. The challenge is explaining where the heat is going. Some process is draining energy from the upper atmosphere faster than solar radiation, auroral heating, and internal heat can replenish it, and nobody knows what that process is. Several hypotheses have been proposed. One suggests that the extreme tilt plays a role. As one pole emerges from 21 years of darkness and begins receiving sunlight, the thermal and chemical response of the atmosphere could drive circulation patterns that redistribute heat in unexpected ways, potentially radiating energy away from the upper atmosphere more efficiently than on a planet with a normal tilt. Another hypothesis connects the cooling to the unusual magnetic field geometry. The tilted offset field produces auroras in different locations and with different energy distributions than on other planets. If the auroral energy is deposited at altitudes where it is radiated away rather than conducted downward, the net effect could be atmospheric cooling rather than heating. A third possibility is more fundamental. Uranus may simply have less internal heat to contribute than the other giant planets. The catastrophic impacts that tilted the planet may have also disrupted the normal process of internal heat transport, creating a stratified interior where hot material in the deep layers cannot convect upward to warm the atmosphere. In this scenario, Uranus is not losing heat anomalously. It never had the internal heat source that the other giants do, and the cooling trend reflects the gradual loss of whatever residual heat remained. Webb cannot distinguish between these hypotheses alone. The temperature measurements it provides are essential, but solving the mystery will require data from inside the atmosphere, measurements of the deep thermal structure, the composition at different pressure levels, and the wind patterns that transport energy from one region to another. Those measurements can only come from a probe descending through the clouds or an orbiter studying the planet from close range over an extended period. The cooling mystery is one example of a broader pattern. At almost every level of investigation, Uranus raises questions that Webb can identify but not fully answer. The auroras trace the magnetic field's influence on the atmosphere, but understanding the magnetic field itself requires in situ measurements from within the magnetosphere. The moons show evidence of subsurface oceans, but confirming those oceans requires gravity measurements and close-range surface mapping. The rings reveal complex dynamics between moonlets and debris, but determining whether the ring system is ancient or recently formed requires compositional analysis that can only be done from orbit. Webb has performed a transformation of understanding. It has demolished the Voyager era portrait and replaced it with something far more complex, far more active, and far more scientifically rich. But it has also exposed how much remains unknown. Every answer it provides opens 3 new questions. Every feature it resolves reveals finer structures that it cannot quite make out. The telescope has taken Uranus from a planet we thought we understood to a planet we know we do not, and that shift in awareness may be the most valuable scientific contribution of all. Because here is the deeper lesson, the one that extends beyond Uranus itself. For nearly 40 years, an entire planet sat in our solar system, orbiting at a distance that light can cross in under 3 hours, and we convinced ourselves it was boring. We had one photograph, one flyby, one dataset collected under anomalous conditions, and we built a consensus, published papers, wrote textbooks, and moved on. Then a better instrument looked, and the consensus collapsed overnight. The rings were there all along. The storms were there. The auroras were there. The polar cap was there. The moons were there, possible oceans were there. The lopsided magnetic field was doing its chaotic dance every 17 hours, wobbling and twisting through space, producing the most asymmetric magnetosphere in the solar system. All of it was happening. All of it was real. We just were not looking. That failure is not unique to Uranus. It is a pattern that recurs throughout the history of science. We observe something once, under limited conditions, with limited tools, and we mistake that observation for the complete truth. We fill in the gaps with assumptions, and those assumptions calcify into received wisdom. Then, when a better instrument or a more sustained observation reveals the reality, we are forced to confront how much of what we believed was constructed from insufficient evidence. Uranus is the most vivid example of this pattern in modern planetary science. But it is also a warning. If we can be this wrong about a planet in our own solar system, a world we can point a telescope at any night of the year, a world whose light reaches us in less than 3 hours, what are we getting wrong about the worlds we cannot visit at all? The nearly 2,000 sub-Neptune-sized exoplanets in our catalogues are described using models built on our understanding of Uranus and Neptune. If that understanding is fundamentally incomplete, which Webb has now shown it to be, then our models of those distant worlds are built on the same shaky foundation. The atmospheric compositions we predict for them, the magnetic environments we assume, the habitability assessments we run for their moons, all of it inherits the uncertainty that Uranus now embodies. Consider a specific example. The exoplanet K218b, orbiting a red dwarf star roughly 120 light-years from Earth, has been one of the most discussed targets in exoplanet science since Webb detected carbon dioxide and methane in its atmosphere in 2023. The planet is roughly 8.5 times the mass of Earth, placing it squarely in the sub-Neptune category. Some researchers have interpreted the atmospheric chemistry as consistent with a world that has a liquid water ocean beneath a hydrogen-rich atmosphere. Others argue the same chemical signatures could be produced by a planet with no ocean at all. Just a thick, deep atmosphere with the right pressure and temperature conditions to produce those molecules abiotically. The debate hinges partly on assumptions about how sub-Neptune atmospheres work, how they transport heat, how they interact with interior layers, and how their chemistry evolves over billions of years. Those assumptions are in every case informed by our models of Uranus and Neptune. If Uranus's actual atmospheric behavior, its unexplained cooling, its heat transport anomalies, its response to seasonal forcing differs from the models we have been using, then the predictions we make about K218b and every other sub-Neptune in the catalogue carry the same error. We are not just extrapolating. We are extrapolating from an incomplete picture of the template world, applying uncertain physics to thousands of distant planets we cannot visit, and treating the results as though they rest on solid ground. Getting Uranus right is not academic. It is the prerequisite for getting a meaningful fraction of the galaxy's planets right. This is not a reason for despair. It is a reason for urgency. The Uranus orbiter and probe is not just a mission to study one planet. It is a mission to recalibrate our understanding of the most common type of planet in the galaxy. Every measurement it returns will propagate outward through the models, improving our predictions for worlds we may never visit, but need to understand if we are to make any meaningful claim about the nature of planetary systems beyond our own. And in the meantime, Webb continues to watch. The telescope will observe Uranus through its approach to solstice in 2028 and beyond, tracking the evolution of the polar cap, monitoring the atmospheric storms, watching the auroras shift as the magnetic field wobbles, and searching for new moons hidden among the rings. Each observation adds to a growing portrait of a world that refuses to be simple. The horror of what Webb has revealed is not contained in any single image. It is not the rings, though they are beautiful. It is not the auroras, though they are strange. It is not the moons with their hidden oceans, though they are compelling. The horror is the realization that we declared a planet understood on the basis of almost no evidence. And then we stopped looking for 40 years. The most unsettling truth about Uranus is not that it is strange. Strange can be catalogued, studied, and eventually explained. The most unsettling truth is that it looked normal. It looked calm. It looked boring. And it looked that way because we could barely see it. We confused the limits of our instruments with the limits of reality. We mistook our inability to detect complexity for the absence of complexity. And we let that mistake stand, unchallenged, for the better part of 4 decades. Uranus was never the quiet ice giant at the edge of the system. It was a tilted, ringed, stormy, magnetically chaotic world with 29 moons, possible subsurface oceans, an atmosphere that is inexplicably cooling, and auroras that sweep across its face in patterns shaped by a magnetic field so distorted it has no parallel anywhere else in the solar system. All of that was there. Every day, every year, every decade that we were not looking. The lesson Uranus teaches is not about one planet. It is about the difference between looking and seeing. Voyager looked, Webb sees, and the distance between those two verbs contains everything we missed, everything we assumed, everything we built on a foundation of 5.5 hours of data taken during a storm. When the Uranus orbiter and probe finally arrives, if it arrives, it will spend years in the system. It will map the magnetic field through thousands of rotations. It will watch the seasons change. It will fly past the moons and measure their gravity. It will drop a probe into the atmosphere and listen to the winds. And what it finds will almost certainly surprise us again, because that is what Uranus does. Every time we look more carefully, the planet turns out to be more than we expected. The real question is not what Webb saw when it looked at Uranus. The real question is what else in the solar system, what else in the universe is sitting in plain sight, looking simple, looking quiet, looking resolved, while something far stranger hides just beneath the surface of what our instruments can show us. Uranus answered that question the only way a planet can. Not with words, not with signals, but by being exactly what it always was and waiting for someone to finally build a telescope good enough to notice. The pale blue marble was a mask. Webb pulled it away. And behind it was a world we are only beginning to understand. The instruments are running, the solstice is approaching, and for the first time in the history of human observation, someone is watching.